Welcome back to MV Tutors. I hope you're doing good. We're going to look at Physical Sciences, Physics Paper 1 that was written in November of 2023. Alright, please don't forget to like our videos and subscribe to our channel. Let's get right to it with question 1, which is the multiple choice questions. Alright, you can either you should actually get a whole lot of your marks from here. I know sometimes the answers might look similar, but I believe you can do it. Alright, so 1.1 says a constant net force is applied to a block. Which one of the following statements is correct? The block will move with a constant velocity, or B, constant acceleration, C, constantly increasing acceleration, D, constantly decreasing acceleration. Okay, so a net force, a constant net force is applied. What is our net force formula? The simple one that we have here is mass times acceleration, right? And we know that the force is actually directly proportional to acceleration, okay? Newton's laws, right? So now here, will it move with constant velocity? Constant velocity means that our acceleration is 0. And if our acceleration is 0, it means that the force applied is 0. So that can't be the case. Constant acceleration, yes. If it's constant force, I would go with constant acceleration. Constantly increasing acceleration, they would have said the force is constantly increasing. Okay? Constantly decreasing acceleration, no, they didn't say anything about it slowing down or speeding up. So the answer here that I would go with is B, because the net force is directly proportional to acceleration. 1.2, a crate of mass m is stationary on a plane inclined at an angle theta with the horizontal. Okay, so I am already in a mode of drawing the the forces around it. But anyway, let's read the question. Which one of the following statements regarding the magnitude of the frictional force acting on the crate is correct? Okay, in order for me to even look at the options before that, can we just draw a free body diagram so that we can see what forces are acting on it? Okay, so always acting downwards, that's the weight or gravitational force. Always acting perpendicular is your normal force. All right, if you were to, okay, it's stationary, right? But it's more inclined to go down, so your friction would be acting in the other direction. Okay, so for now it's static friction. And then if you were to put your gravitational force in its components, this would be Fg cos theta, or your perpendicular component, and that would be your Fg sine theta, or your parallel component. Okay, now let's go back to our blue pen. What are they saying about the magnitude of the frictional force acting on the plane? So it is equal to the component of the weight of which the crate, the weight of the crate which is parallel to the plane. Yes, that's correct. B, it is larger than the component of the weight of the crate which is parallel to the plane. If it was larger, it would be moving upwards, right? There would be movement. So the fact that it is stationary, it means that they're equal. C, equal to the component of the weight of the crane, which is perpendicular. No, that is the normal force. And larger than the component of the weight of the crate, which is perpendicular. No. So we're just looking at the parallel component, and it must be equal to. So I would go with A. All right, 1.3. A ball is projected vertically upwards from the top edge of a building. So it's projected vertically, right? There's an initial velocity. Points P, Q, R, and S represent different positions during the motion of the ball, as shown in the diagram below. All right? Ignore the effects of air friction. So between which 2 points will the ball undergo the greatest change in kinetic energy? I would like for us to just sketch this again. Okay, just make it a bit bigger. So here, as they are about, okay, let's just also put in PQRS. And let's talk about So here there is an initial velocity. There we know our velocity is 0. At point R, our velocity will be equal to the initial velocity, and point S, there you'll get your maximum velocity. So because there's an initial velocity, we do have kinetic energy, right? Potential energy here is 0. Well, it depends. It depends. If you're referencing the ground, then there is some potential energy. But if the top of the building is your reference, then there isn't potential energy. So let's not talk about potential energy for now, so that we can avoid confusing ourselves. We're focusing on kinetic energy because they ask between which 2 points will the ball undergo the greatest change in kinetic energy. Remember, change in kinetic energy is your final minus your initial. All right, so we have some potential energy over here. There your potential energy is 0 because your velocity is 0. Your kinetic energy over here is equal to the one at P. Okay. And then here at the bottom, you have like your maximum potential energy because your velocity is your maximum. So let's see. Between P and S, here's the thing. Our initial kinetic energy over here, well, it will go up and it will go down. So they will sort of like cancel each other at that point. So I don't think all the way from P to S, the only kinetic energy I would consider is here. So that can't be the greatest change. And then between P and R, that one they will cancel each other out because you have it going up and have it going down, so it will be 0. R and S, where's R and S? So this point over here is pretty much equal to option A, which is between P and S. All right, so at this point, that is the greatest change that we have from the options given. And then D, between Q and S, yes, definitely, because you have your maximum here and you have 0 over here. So the change there, if you're going to subtract 0, you're left with your maximum, okay? So your final is a maximum, initial is 0, so that would be the greatest change in kinetic energy. So I would go with option D. And then 1.4. Now a ball is dropped from height h and strikes the floor with momentum p. Okay, if it's dropped, we know that the initial velocity is 0. The ball is then dropped from height half of h. Okay, so we have our full height and we have half the height. Now what are they going to ask us? We have 2 scenarios. Okay, now it says ignore the effects of air friction. Which one of the following represents the momentum of the ball when it strikes the floor after being dropped from half the height? Okay, we're going to look at these scenarios differently. So we have the full height. Okay, so with the full height, momentum, what is momentum? Momentum is just mass times velocity. Now, how does height get in? Well, if we were to write this somehow in terms of height, that would help us a lot. Okay, how about we use one of the equations of motion just to see, can we use anything from there? That would have height in it. Okay, and that we don't want time in that equation. So let's go for velocity, final velocity squared. Okay, let me just write this in the middle just so that we can show that we are thinking about this. So final velocity squared is equal to initial velocity squared plus 2 acceleration. I'm just going to say gravitational acceleration and delta y. Okay, that is basically our height. Let me just remove delta y and put there h, because we want height somewhere, because the question is about height. All right, so okay, how can we rearrange this? So we know our initial velocity is 0, right? Because it was dropped in both scenarios. So I have final velocity squared is equal to 2 times gravitational acceleration times the height. And my velocity then, I'm just going to say velocity, is the root of 2gh. Okay, so in this case, for the full height, I have that momentum is equal to mass times velocity is root 2gh. Okay, looking at my options here though, I'm seeing root 2, 1 over root 2, half p, blah, blah, blah. Let's just leave it at that for now for the full height. Now let's look at half the height. Okay, so with half the height, my momentum would be mass times the velocity. Well, this time, velocity here, let's say final velocity squared would be equal to 2g and half the height. Okay, so the half and the 2 would cancel, so I have just g. So velocity is root g. Oh, forgot the h, half the height. It's just root gh. Okay, so I can put it there in terms of the velocity is root gh. Okay, so now how am I going to equate this? So it says, what is it if now we have half h? Okay, so this is for half and this is for the full height. So I see here my momentum on the full height. I'm leaning towards B, but I need to find a way of writing it in terms of 1 over root 2. So this is what the momentum is if it's half the height. Okay, but if I were to, let me just see, if I say momentum times root 2 times root gh, you know from maths we can actually do that, right? So basically I would have momentum is root 2 and then I have m root gh. Okay, so I have momentum written in this form, and I see here my momentum when it's half the height. Okay, so I see this portion over here and I see that portion over there. But what's the difference between the two? Okay, the difference is I need to then take this root and take it to the other side. So I'm going to have 1 over root 2 p is m gh. Okay, so that's basically what would happen. That would be 1 over root 2 p is equal to m gh. Okay, because we know that m gh, that is halfway. That is when the height is half. Okay, and so in order for that to be the case, we need to have 1 over root 2 p. Geez, I hope I didn't confuse you guys, but yes, that's how we conclude this question. So in this case, the answer would be B. That was a bit tricky, I have to say. Okay, now let's move on to 1.5. So it says, a box moves on a horizontal surface. The diagram below shows all the forces acting on the box. Okay, so we can see our force Q over there. P and R sort of like cancel each other out. I would say S would be a friction force. We don't know. We just, predicting or just assuming. Now it says, which one of the following combinations of forces do work on the box? All right. So as soon as I start hearing the word work, I'm not even going to consider P and R, because vertically, if you have a force that's like pulling, especially like this diagonally, if we resolve it into its components, we have a vertical and a horizontal. It's the horizontal component that will do work. So vertical, I'm not even going to consider it. Okay, so P and R, I'm canceling out of my mind. Anything to do with P and R, basically. So if I'm taking out P and R from my mind, A will not work, C will not work, and D will not work. So B has to be the correct answer, which is Q and S only. Yes, because there's work done due to friction. Okay, that's the non-conservative force, friction, and then Q as well. So that's the only thing. Anything vertical does not work in this scenario, so I would choose B. Then 1.6. All right, it says a train moving at a constant velocity towards a stationary listener emits sound waves of constant frequency. Which one of the following statements about the sound waves observed by the listener is correct? Okay, so observed by the listener. The frequency is higher than the emitted frequency. The wavelength is longer than the emitted frequency. The frequency is lower than the emitted frequency, or D, wavelength is equal to the emitted wavelength. Okay, so you have a train moving towards a stationary listener. If you have your stationary listener over here and the train is busy moving towards the stationary listener, as it moves towards them, the wavelengths, okay, they start out big, but then they start now becoming smaller. Why? The wavelengths, as they reduce, your frequency becomes higher. And therefore, as the train moves towards the listener, what the listener will hear, the sound will be more, basically, for the listener. If the train moves past the listener, the wavelengths are going to be big. Okay, so therefore, the wavelengths here would be increased and the frequency will be lower, and that is why the listener will hear the train less as it moves away. So here, the frequency is high, the wavelength is low. So A, frequency is higher than the emitted frequency, yes. B, wavelength is longer, no. Frequency is lower, no. Wavelength is equal, no. So A here would be our correct answer. 1.7. Okay, refer to the diagram below. Q and R are small spheres suspended by light insulated strings. When a negatively charged rod is brought close to sphere Q is repelled. Okay, all right, so what does that tell us about Q? I'm thinking that Q is negatively charged. When the negatively charged rod is brought close to sphere R is attracted. Okay, that's nice. What does it tell us about R? Well, I'm thinking from, the top of my head, it's positive. All right, now let's see. Which one of the combinations below can be possible for the nature of the charges on sphere Q and R? Okay, so Q, I'm only going to look at the negative options, okay? Okay, so C says neutral. Okay, anyway, let's focus. It's either A or D. And the nature of charge on sphere R, we said it's positive, so we're looking at C. I'm seeing neutral. Okay, guys, here's the thing. So when it comes to charges that are repelling, if they repel, both of them either need to be negative or both of them need to be positive. So here we're dealing with negative charges, right? So Q definitely is negative. So A and D, I'm sticking my guns to it. It cannot be neutral. But the one thing I have forgotten is when it comes to forces of attraction, you either have a negative and a positive, right? So hence, when the rod was negatively charged, I assumed that it's positive. Positive is the correct answer, but also a neutral charge will also attract a negative charge. Okay, so it can either be positive, R can either be positive, or R can be neutral. Okay, yeah, that's one thing I had forgotten. So yes, positive or neutral can attract negative. So in this case, because I'm sure of A and D, I need to look for neutral for sphere R, since positive doesn't work. So for A, it cannot be negative. D, I see this neutral. So actually D is the correct answer. Okay. All right, 1.8. We are almost there. 3 more questions. Okay. So it says, okay. Four voltmeters V1, V2, V3, and V4 are connected in a circuit as shown in the diagram below. Which voltmeters will have the same reading as voltmeter V1 when the switch is open? Alright, so when the switch is open, we can see the positive terminal is this side and the negative is there. So the current will be flowing in this direction, right? Okay, so there V4 will be the current multiplied by whatever resistance that's there, but that's across the ammeter. I don't think the resistance is too high. It's almost negligible. But V4 is opposite V2. So whatever you get for V2, it'll actually be opposite. It'll actually be equal to V4. And V2 over here, well, the switch there is open. So the current is only going to end up here before the switch. So, actually, yeah. There you have your positive, you have your negative, but the current over here will have broken, okay, because the switch is open. So even for V2, I'm kind of like, will the current still be going through? It won't because the switch is open. So V2, I would say it's also 0. So V4, V2, they're close to each other. They're almost 0 because they're parallel, so they're equal. And because I said this resistance through an ammeter is negligible, I would say there's 0. So I don't think V1 will be equal to that. But V1 can be equal to V3. Why? Remember, when it comes to parallel connections, the velocities, the voltmeter readings, the potential difference is the same for those that are parallel. Okay, so V1 in this case would be equal to V3. Tell me what you think. Do you agree or not? So options A, V2 only, no. V3 only, I would go with that. V4 only, no. V2 and V4 still makes no difference. So I would go with option B. All right. And then now 1.9. So it says a split ring commutator connects the coil of a generator to an external circuit. Okay, so split ring commutator, that should remind you of DC. All right, voltage, and then generator. I don't know if you're going to need this, but I'm thinking of the right hand rule just in case you're going to need it. And then to an external circuit. Okay, which one of the following, or which one of the combinations below is correct for the magnitude and direction of the induced current in the external circuit? Okay, so when it comes to direct current, what happens to, direct current, remember, its graph, if this is now your positive V, that's your negative V, that's your time. Its graph will look like this. Whereas with your AC, it will be like a sine graph. It's more sinusoidal. Okay, it's negative V. All right, so now the magnitude of the induced current. Do you see that it will start, okay, that's voltage, what I've drawn, but also the current follows the same pattern. So even if I did current over here, okay, still the same. So with direct current, it changes. The magnitude of the induced current it changes. If it were constant, you would have something like this. Okay, either some value over there. It would be constant, but we're seeing it changes because if you read it over time, you can see it changes. Okay, but the direction of the induced current, that one is constant. The one that changes is this, the alternating current. That the direction changes, okay, for alternating current, but the direction for direct current, that stays the same. Okay, so looking at our options here, we said the magnitude of the induced current, we said it changes, so we have options C and D. but the direction of the induced current, it remains the same. So it's constant. So we have A and C. That's our option. So basically, C is the correct answer. Again, lastly, question 1.10. Light of a suitable frequency is shone on the surface of a metal and electrons are ejected from the metal. Okay, this is photoelectric effect. So now, which one of the following is equal to the ratio of the work function to the threshold frequency of the metal? Okay, so remember this is work function and we have threshold frequency. Can we get the equations over there just to see? It's going to take forever. But yeah, please do not be shy to consult your formula sheet. You don't want to be choosing incorrect things. Okay, so what equation there has work function that also has threshold frequency? Well, I see there work function is equal to Planck's constant times the threshold frequency, and they asked for the ratio of the work function to the threshold frequency. So that's equal to Planck's constant. All right, now let's go back up. This might take a while. I even forgot what the question is, but I'm also question 9. So going back to question 1.10. Please just bear with me a little bit. Okay, so it says which one of the following is equal to the ratio of the work function to the threshold frequency? We can see here it's equal to Planck's constant. So A would be the correct answer, but let's read the others. The inverse of Planck's constant, no. The energy of the incident photons, no. The maximum energy or kinetic energy of the ejected electrons, no. So we're going to go with Planck's constant, and we are done with question 1. 20 marks. How much time should you have spent on this question? We have 180 minutes, 150 marks. Multiplied by 20 marks, you could have spent 24 minutes on this question. Question 2. Two blocks A of mass 4 kg and B of mass 9 kg are connected by a light inextensible string. The blocks are held at rest on a plane which is inclined at an angle of 35 degrees with the horizontal. A constant force F acting parallel to the plane is applied to block B, as shown in the diagram below. Now the blocks accelerate up the plane at 2 meters per second. Okay, so initially they were at rest, but now with this force, this constant force, we have a constant acceleration of 2 meters per second. Okay, so 2.1. State Newton's second law of motion in words. If you can just think about this equation, the net force is equal to mass times acceleration. That will actually help you to state Newton's second law of motion, of motion in words. So what does it say? It says when a net force acts on an object, the object will accelerate in the direction of the force. Okay, and what about that acceleration? Well, that acceleration is directly proportional to the net force. And what else? That acceleration is inversely proportional to the mass of the object. Okay, so that's just that for 2 marks. Make sure you know your definitions. 2.2, so before we get to the question, it says the kinetic frictional forces acting on blocks A and B are 5,88 Newton and 13,23 Newton. Okay, so kinetic frictional force for A, just write it down for yourself, 5,88 Newton, and we also have for B, which is 13,23 Newton, just so that you have it there for yourself. Now it says, okay, let me just erase this. Alright, so now we can start with 2.2. So it says draw a labeled free body diagram showing all the forces acting on block A. Alright, so if this is your inclined plane, so that's A. Firstly, we're going to obviously start with the weight or your gravitational force, and then perpendicular to that you have your normal force. There's the tension force, from the string. But also, since the force is going upwards, we're expecting the frictional force to actually go down, right? Because it is friction always opposes motion. Okay, and how many marks? Normally, the free body diagram tells you, the mark allocation tells you how many forces you should have. If you wanted to put in the components of your gravitational force, you could have. Okay, so that would just be the perpendicular component, or you could have said Fg cos 35 degrees, and you would have also the horizontal component, which is just Fg parallel. I'm just going to leave it at that, or it could be Fg sine 35 degrees. Okay, but those four forces by themselves, that is pretty fine. Okay, now 2.3, it says calculate the magnitude of the tension in the string. Okay, so that is in between block A and block B. Remember, this is for block A. Tension in the string, how many marks? That is 4 marks. I would also draw the free body diagram for B, just for myself. Okay, so I'm just going to put it there. 2.3, let's put in the free body diagram. We're going to need it, right? So for B, I'm just going to put it there. All right, so we have the force of gravity going down. We have our normal force. We have our applied force. We have the tension in the string. Okay, it's not exactly parallel, this applied force, but you get it. Tension in the string. We also have the friction force. All right. Are we missing anything? Well, if you were to resolve the force of gravity in its components, you would do exactly that. That also forms part. Oh, so many things happening there. So yeah, that's it. But this is not for marks. Remember, this is just you doing it for yourself. Now, if we're going to get the tension in the string, how are we going to calculate that for 2.3.1? Well, we're going to say the net force using Newton's second law is equal to mass times acceleration. Okay, and if I can just use block A for now. So if I'm going to use the free body diagram, I have tension in the positive direction, and I have friction as well as the component of gravitational force in the opposite directions. So let's put that in place. So tension minus our frictional force for A minus our gravitational force, the component, the parallel component. So that's the net force acting on it, and that is equal to mass times acceleration. All right, so please don't be troubled by the extra breathing here. I'm not alone. So now what are we looking for? We're looking for the tension in the string. So I'm going to put everything in terms of tension and take everything to the other side. So I have the frictional force for A. All right, we wrote that down. It is 5,88. So if I take friction force to the right side of the equation, I have 5,88, and the parallel component of the gravitational force. Well, what's gravitational force? That is just mass times gravitational acceleration. So we're looking at the 4 kilogram block. So that's 4 times 9,8. All right, and that will be also multiplied by sine 35 degrees, and then we have our mass times acceleration. So our mass again is 4, and how much is our acceleration? They told us that it is 2, so that's just 4 times 2. Okay, so we can put all of this in the calculator. So we have 5,88 plus 4 times 9 comma 8 times sine 35 plus 4 times 2, which is just 8. Ooh, no, what have I been doing? 5 comma 8, 8 plus. Oh my word, I'm thinking this is a lot. 5 comma 8, 8 plus 4 times 9 comma 8 times sine 35 plus 4 times 2, which is 8. Okay, that looks much better. So the tension in the string is actually 36,36 Newton. Okay, great. So that was 2,3,1. Now 2,3,2. So now it says calculate the force F. Okay, for that I'm going to need block B. That's why I was saying please just draw for yourself so that you can easily refer to it. Okay, so now for block B, I'm also going to use the net force, which is equal to mass times acceleration. So what is the net force? Looking over here, we have the force applied, right? Minus the frictional force, minus the tension, minus the horizontal component or the parallel component of the frictional, the gravitational force. Okay, so let's write it down. We have the force applied minus the frictional force for B, minus the tension, minus the parallel component, that is equal to mass times acceleration, and we're looking for force applied. Okay, so I'm just gonna put it as F because they gave it to us as force F. Okay, so that is equal then, let me start with the mass times acceleration plus the frictional force plus the tension plus the parallel component. Now what is the mass? 9 times 2, because that's the acceleration, that's 2. And then we have the frictional force for B, we wrote it down, it is 13,23. And then the tension, we calculated it previously, 36,36. So if you got it wrong, yeah, it will mess up your answer, but they will give you they will mark you right because at least you have the formula right, but the final answer will definitely be wrong. And then you have the parallel component, so FG, that's simply 9 times 9,8, and then we have times sine 35 degrees. Okay, so now we can get the force. So we have 18 plus 13,23 plus the answer plus 9 times 9,8 times sine 35 degrees, and we get an answer of 118,118 Newton. Okay, so we leave it at that, and then we're almost there. So 2.4, the angle that the plane makes with the horizontal is now decreased. So we're going now from assuming that's 35, quite steep for 35, but for demonstration purposes, now we are reducing it. It's decreasing to whatever that value is. Okay, so now 2.4.1, it says, how will this change the kinetic frictional force acting on block A? Okay, choose from increase, decrease, or remain the same. Okay, so I will go with increase. And then now 2.4.2, we need to explain the answer to question 2.4.1. So kinetic frictional force, right? So that is just, it's equal to our constant there multiplied by the normal force. All right, and remember, when it comes to the normal force, okay, so basically frictional force is directly proportional to your normal force. Let's just put it there. Your normal force let's just go back to the free body diagram here. Your normal force is related actually to your cos, your angle, 35 degrees. Okay, so if you reduce the angle, let's just say this is what, 4 kilogram. So we have 4 times 9,8 times sine 35. What answer do we get? We get 22,48. Now if we decrease sine 35, we make it now, no, I'm using the wrong one. 4 times 9,8 times cos, because we're looking at the perpendicular component. So we have cos 35. So our answer would be 32,11. Now what if we reduce it now? This is from cos 35 to cos 30. Your answer is 33. Do you see that it's increasing? Let's go again. Let's try 35 again. So we have 32. 32, let's go to 25. We have 35. Okay, so basically, when you increase or decrease rather, if you're going to decrease theta, you're actually going to increase your normal force. Okay, because your normal force is equal to the perpendicular component of your gravitational force. So as a result, decreasing the angle will increase your normal force, which will in effect increase your frictional force. Okay, I hope you followed and you saw. All right, so yeah, that is that, and we are done with question 2. It was 16 marks, so 16 times 1,2 should have spent what, 19,2 minutes. Let's see, where are we? We're at 14 minutes, so we saved some time. Question 3 looks like vertical projectile motion. So a ball of mass 0,5 kilogram is thrown vertically upwards from the top edge of a building which is 15,3 meters high. All right, so it is thrown, meaning there's an initial velocity. The ball reaches a maximum height of 5,89 above the top of the building. The ball strikes the ground and bounces vertically upwards, reaching a maximum height at point P as shown in the diagram below. All right, so ignore the effects of air friction and define the term free fall. So free fall is basically when a projectile is, I don't want to say falling. I'm just going to define it loosely. So it's when a projectile has no other force but gravitational force acting on it. All right. And then 3.2. Using only equations of motion, calculate the speed at which the ball was projected upwards. So basically we're looking for the initial velocity, right? And what do we have at the moment? So yeah, we're just going to note the things that we have. We know that from the point it was thrown until it reaches its maximum height where the velocity is 0, that at that point in time delta y is 5,89. But it really depends. Are you taking upwards as positive or negative? So in this case, let's take upwards as positive. So yes, delta y is going to be positive 5,89 meters. And let's go and have a look at the equations of motion to see which formula we're going to use. Right, so here we are. We have our initial velocity. No, we're looking for it. We have our final velocity, and we have our delta y. We don't have time, so the only equation that makes sense would be using final velocity squared is equal to initial velocity squared plus 2g delta y. All right, let's go back to the question. Question 3. Okay, so there we are, page 9. All right, so our final velocity, we did say it is 0. And our initial velocity is what we're looking for. And then our gravitational acceleration, well, basically, because it's always acting downwards, we're going to have to put a negative 9,8. And our delta y in this case is 5,89. All right, so our initial velocity is equal to 5,89. So the negatives cancel, and if I take the root of 2 times 9,8 times 5,89, what answer do I get? Square root of 2 times 9,8 times 5,89 gives me an answer of 10,74, and that is the initial velocity. Okay, let me take a little break and attend to my little friend. Alright, 3.3. So it says, after the collision with the ground, the ball leaves the ground with a speed of 11,92 meters per second. So let's just, do this. Alright, so we know that the ball left here with the velocity of 10,74, and then at its maximum it reaches 0, and then it passes the top of the building again, and when it does that, it still has the same velocity of 10,74. Then it gets to the ground with some velocity, right? We know that it's V max, and then because it gets in touch with the ground, loses some of its energy, it leaves the ground with the velocity of 11,92 meters per second, and then it reaches its maximum height at P, where velocity is 0. So 3.3.1, it says calculate the amount of kinetic energy lost by the ball during the collision with the ground. So what I'm interested in, I want to know what this maximum velocity is, okay? And so yeah, let's start there, because we would know the velocity coming in, the velocity going out, and then we can calculate then the kinetic energy that is lost. Alright, so I think we're going to use the same equation that we used previously. Alright, because we have initial velocity, which is 0. Final velocity is what we're looking for. And the height, the height. So I'm going to look at this height from the top all the way to the bottom. Okay, so let me just write all the information that I know. I know initial velocity is 0. I know I'm looking for my final velocity. And my delta y in this case is 5,89 plus 15,3. So what is 5,89 plus 15,3? That's, no, what did I write? Oh, why am I saying multiply? My goodness, plus. So that's 21,19 meters. Okay, but now everything is going down. Let's just write the equation. Final velocity squared. So this is just information for ourselves. So final velocity squared is equal to initial velocity squared plus 2 times gravitational acceleration times delta y. Because we chose upward as positive, okay, we're going down, right? Our initial velocity is 0. Our gravitational acceleration is going to be negative because we chose upwards as positive. And our delta y is also going to be negative because now we're going all the way down. All right, all the way down. So it'll be negative 21,19. Okay, and now in order to get our final velocity, that will basically be the root of 2 times 9,8 because the negative and the negative, they'll cancel out and be positive. And then 21,19. Alright, so now square root of 2 times 9,8 times 21,19, and that gives us a maximum velocity there at the ground of 20,38 meters per second. So that is the Vmax over there, 20,38. And now it leaves with 11,92. So there's some 20,38 minus 11,92, that's lost there. So now let's look, because they asked us for energy, right? Amount of kinetic energy lost. So now let's calculate by using our formula, our change in kinetic energy, which is equal to half times the mass, and we have final velocity squared minus initial velocity squared. Remember, please do not write it like this. It is wrong. Okay, absolutely wrong. All right, let me just erase that. Yeah. So now we have half. They told us the mass at the beginning of the question, which is 0.5 kilograms. Our final velocity, well, basically, yeah, we're going to take that. Remember, upwards is positive, right? Our final velocity, I'm going to take it as the lift off velocity. Okay, so as it's lifting up, which is 11.92 seconds, and our initial velocity, actually, let me do it the other way. Okay. Yeah. Because, yeah, this is velocity coming down and then going up. Which one should I take as the final velocity and then the initial velocity? The final should be the lift off. The initial should be the max. Yeah. So 11.92 squared minus 20.38 squared. But this is a negative because it's going down, but it doesn't matter because it will be squared. Okay, now I'm thinking this change in energy is actually going to be negative. What does the negative tell us? So 0.5 times 0.5 times 11.92 squared minus negative 20.38 squared. Yeah, this is a negative energy. Yeah, but this energy lost. So we have negative 68.31 joules. So basically, the energy lost is 68.31 joules. That was lost. Yes, that's the energy that was lost. 68.31 joules. All right, and then 3.3.2. It says the time taken for the ball to reach point P after leaving the ground. Okay, so our initial velocity then will be 11.92 and our final will be 0. But now we need an equation that incorporates time in it. Okay, so let's see. Equations of motion, final velocity, initial velocity, time. That's the first equation that I'm seeing there. So final velocity is equal to initial velocity plus gravitational acceleration, and we're multiplying it by time. So our final velocity is 0. Our initial velocity is what they told us there, which is 11.92. Let me just see again. $11.92 plus, remember, down is positive, 9.8, and the time is what we need. So basically it will be 11.92 over negative 9.8. If I take the 11.92 that side, it's negative, and I'm going to divide by that as well. Hence, double negative. Okay, so now 11.92 or negative 11.92 divided by negative 9.8, that's equal to 1.22 seconds. Alright, so that's the time taken for the ball to reach point P. Okay, now 3.4. It says that velocity time graph for the motion of the ball from the instant it is projected upwards from the top edge of the building until the time it reaches point P is shown below. And we're going to have to write down the numerical values indicated by each of the following. Okay, just want to make some marks there, but let's look at our drawing over here. So this is basically at time 0. So this is time 0, and yeah, let's rather just use this. So at time 0, our velocity was 10,74. Okay, and then here we reached 0 velocity at whatever time that is, and then here that's where the ball bounces. All right, but what's that velocity? It went down with 20,38, and then it lifted off with 11,92, and we know that the time it took from 11,92 to 0, that's the time that we calculated now, right, which is 1,22 seconds. All right, so now let us answer the questions for 3.4. So 3.4.1, K, that value is 11,92 meters per second. That was given to us. All right, and then 3.4.2, that is L, so that's 10,74. That's what we calculated. So L is 10,74 meters per second. So that's K. And then the last question, 3,4,3, the difference between time 2 and time 1. Okay, that is 1,22 seconds. All right, so that's basically that. And that is the end of question 3. Thank you for joining us. See you in question 4. Question 4. A wooden trolley of mass 2,7 kilograms moves to the left with a constant velocity of 3 meters per second. Okay. A bullet of mass 0,03 kilograms is fired horizontally from the left towards the trolley. Now, as you can see, there's diagram 1 and then diagram 2. That bullet, as tiny as it is, it comes in with such a high velocity, it will definitely cause the trolley to move in the opposite direction of the collision. Anyway, the bullet strikes the trolley and comes to rest inside the trolley in 0,2 seconds. The average net force exerted by the trolley on the bullet during this time is 591 Newton. The bullet trolley combination now moves to the right. All right, so now it says ignore all frictional and rotational effects. So 4.1, write down the magnitude and direction of the average net force that the bullet exerts on the trolley. Okay, they told us already the average net force exerted by the trolley on the bullet is 591. But now they want to know the average net force that the bullet exerts on the trolley. It's still going to be 591 units, and the direction of it will be to the right. Okay, and 4.2, calculate the magnitude of the velocity with which the bullet strikes the trolley. Okay, so let's have a look at the formula sheet. All right, we can look at momentum before equal to momentum after, but also we have the net force times delta T is equal to delta P. All right, where delta P is the final momentum minus the initial momentum. So let's just go back to the question. Okay, so for 4 marks, calculate the magnitude of the velocity with which the bullet strikes the trolley. So we have the force, we have the time, we have the mass of the trolley as well as the bullet, but now it's the magnitude and velocity with which the bullet strikes the trolley. So it's about to strike the trolley. So in this case, we're only looking at the bullet. Okay, we're not going to add the mass of the trolley in this case. Okay, it's the velocity with which the bullet strikes the trolley. And that's why I'm not using the formula of momentum before is equal to momentum after, because that forces me now to also add the information of the trolley. Okay, so I'm using the net force times time is equal to the change in momentum. All right, so what is that net force? It's 591 multiplied by the time, which is 0.02 seconds. And momentum, remember, it's mass, then you have final velocity minus initial velocity. Okay, we know that eventually it comes to a standstill. So the mass being 0.03 kilogram, final velocity is what we're looking for. No, final velocity is 0. Okay, because it comes to a standstill. Initial velocity is what we're looking for. All right, let me just put this in brackets. Maybe we can use that formula just for the bullet. But anyway, so if I now take 591 and I divide it by 0.03, that would be equal to negative initial velocity. If we're taking right as positive, yeah. Anyway, let us have a look. So calculator here, 591 multiplied by 0.02 over 0 divided by 0.03. Okay, we get an initial velocity, which is negative 394 meters per second. What does this negative mean? Because the bullet is going to the right. Okay, and the force, the average net force exerted by the trolley on the bullet is 591, and the trolley that time is moving to the left, right? And then it says calculate the magnitude of the velocity. Okay, they wanted magnitude. We'll think about this negative another time. But this is 394 meters per second because they want the magnitude. Okay, so I think this net force should be negative because the average net force exerted by the trolley on the bullet was positive 591, meaning positive is in that direction. Okay, and then going to the right means it's more of your negative. Okay, so hence the negative that we calculated there, 394 meters per second. So yeah, I'm wondering now if we had used, momentum before, momentum after, let's not even go there. So we have the initial velocity, 394 meters per second. That does make sense. Okay, it is a high velocity. We're expecting that from a bullet. So that was for 4 marks. In our 4.3, it says, state the principle of conservation of linear momentum in words. Okay, so that's just the theory that you need to know. And the principle of linear momentum states that in an isolated system, so keyword there, isolated system, the total linear momentum remains constant in magnitude and direction. Okay, so basically the total linear momentum will remain constant in magnitude and direction in an isolated system. Okay, so what it's saying there, basically the sum of your initial momentum will be equal to the sum of your final momentum. That's what this principle is basically saying. And now just before they always be aware that whenever they ask for a certain theory, the next question is more the application of the theory. So now it says calculate the magnitude of the velocity of the bullet trolley combination after the collision. Okay, so we are going to use this formula where the sum of the momentum before is equal to the sum of the momentum afterwards. Okay, final. So in this case, we have the mass of the bullet and the velocity of the bullet plus the mass of the trolley times the velocity of the trolley, and all of this is initial, right? Same thing again, mass of bullet, but now they're together, right? As we see in diagram 2. So mass of the bullet and the mass of the trolley, and we're multiplying that by the final velocity. Okay, so what's the mass of the bullet? It is 0.03, and the velocity, we calculated it as 394. The mass of the trolley is 2.7 kilogram, and its velocity was 3. Okay, we said going to the left is positive, to the right is negative, so we should be putting a negative somewhere there. Okay, let's see how that will work out. And then mass of the bullet 0.03 plus mass of the trolley, which is 2.7. And what we're looking for is the final velocity, right? Magnitude of velocity of the bullet trolley combination after the collision. Okay, so final velocity, we'll have negative 0.03 times 394 plus 2.7 times 3 divided by 0.03 plus 2.7. Sorry about that. All right, so negative 0.03 times 394 plus 2.7 times 3, 0.03 plus 2.7. Okay, so I get a final velocity of negative 1.36 meters per second. And what does that tell us? That is basically 1.36 meters per second to the right. Okay, remember velocity is a vector, so magnitude and direction. Okay, and that is it. Are we done with question 4? Yes, we are. Question 5. Learners conduct an experiment to determine how the initial kinetic energy given to a trolley affects the distance the trolley moves on a rough horizontal surface. A learner pushes a trolley of unknown mass until it reaches point A with kinetic energy, EKA. The horizontal distance, delta x, traveled by the trolley before it comes to rest is then measured. See the diagram below. The experiment is repeated with the trolley moving on the same rough horizontal surface, but with different initial kinetic energies at point A. So the results obtained are shown in the graph below. So on the x-axis, we have initial kinetic energy, and on the y-axis, the distance traveled. Okay, so we can see the higher the kinetic energy, the more distance is covered. Okay, so now 5.1, so it says ignore the effects or the rotational effects of the wheels of the trolley. 5.1, draw a labeled free body diagram showing all the forces acting on the trolley during this motion or its motion after passing point A. So after passing point A, there is no force that is applied on the trolley, okay? Because the learner would be pushing it, but in this case, from point A onwards, there is no external force, pushing, pulling, or whatever. So our then free body diagram will have the gravitational force or the weight of the trolley itself. And then in the same light, we have the normal force, all right? And then, since it's going to slow down and eventually stop, that tells us that there is friction. Okay, and there's no applied force after point A. So this is it. All right, and that's 3 marks. 5.2, it says name the independent variable in this experiment. If it's independent, it is normally placed on the x-axis. If it's dependent, it's on the y-axis. So the independent variable in this experiment would be the initial kinetic energy. Initial kinetic energy, okay, which is in joules. And then 5.3, okay. 5.3, state the work energy theorem in words. Okay, by now you know I don't like writing down these definitions because they can be quite long, but the work energy theorem states that the net work done on an object is equal to the change in kinetic energy of the object. Okay, so the net work done on an object is equal to the change in kinetic energy of that object. Okay, that's simply that. If you remember the equation, you'll remember the definition. And then 5.4, which is the last question for 6 marks, it says, calculate the mass of the trolley if the coefficient of kinetic friction between the wheels of the trolley and the rough horizontal surface is 0.18. So mu k, which is our coefficient of kinetic friction, is equal to 0.18. And remember, we're dealing with now friction here. Friction is a non-conservative force, right? So we're going to look at the work done by a non-conservative force, which is equal to the change in kinetic energy plus the change in potential energy. But based on our definition before, we're really not going to even look at the potential energy. I'm just going to write it down because I think according to the formula sheet, this is how it's written. Yeah, for non-conservative force, we have change in potential energy plus change in kinetic energy. But really what we'll be focusing on is the net work done by this friction, and that's the change in kinetic energy. But anyway, let's go back to our question. Question 5.4. Okay, so the work done by the non-conservative force, which is the friction in this case, the net work done by it. Yeah, I should have just said either use this equation or you use this one like I had said in the previous question. If you have a formula beforehand, chances are, if you have a definition beforehand, chances are the formula related to that definition will be used in the next question. So now we have the force of friction, right? But remember the work done, you have force times the distance, delta x times cos theta. Okay, that's the only force from point A onwards, especially where friction is applied. And that is equal to change in kinetic friction, which is half times mass, final velocity squared minus initial velocity squared. And because this is in a straight line, even if you try to incorporate potential energy in it, it'll be 0 because the height is the same. So final height minus initial height will be 0. So the entire potential energy will be just 0. So we're not even going to bother with it. Now, the friction force, the formula for it, remember, it is mu times the normal force. Okay, so we have mu k times the normal force times delta x cos theta half m. We're gonna just fill in the values now. So mu k, they've told us, is 0.18. The normal force is basically going to be the mass times gravitational acceleration, and we don't know what the mass is. That's what we're looking for. So mass times gravitational acceleration, and then delta x. Well, it's up to you. You can look at the graph and you can, use whatever. I'm just going to go with the first values. For a distance of 1,5 meters, we get initial kinetic energy of 6. All right, so cos theta, because it's friction, it will be theta will be 180 degrees. And then you have half, actually, this entire kinetic energy, we can just say it is 6. Okay, it would be 6. Yeah, so your final velocity would be 0. Your initial velocity would be whatever value it is. So in this case, since your final is 0 and your initial is a certain value, your answer there will be negative. Okay, I hope you understand where that is coming from. Okay, if I had the velocities, it would come in at A at a certain velocity, but it would finish off at 0 because it comes to a standstill. So I would have 0 minus some velocity there. So your answer ultimately would be a negative, and hence that's why I'm putting there a negative 6 for our initial kinetic energy. All right. Now our only unknown is m. So let me just put mass by itself and then say negative 6 divided by 0,18 multiplied by 9,8 times 1,5 times cos 180 is actually negative 1. So yeah, times negative 1. So if we work everything out, you have negative 6, 0,18 times 9,8 times 1,5 times negative 1. Okay, and we get an answer for mass of 2,27 kilograms. So that is the mass of the trolley, and we are done with question 5. All right, we've done the first half of this paper. Now we're left with the last half. Now, 6.1. An ambulance is moving away from a stationary listener, okay, with a constant velocity of 25 meters per second. The siren of the ambulance emits sound waves at a frequency of 550 hertz. The listener detects frequency of these sound waves to be 512,64 hertz. So you have this listener over here, stationary listener, meaning the velocity there is 0 meters per second. And the frequency that the listener hears is 512,64 hertz. Whereas now we have this ambulance over here, which is moving away. And, yeah. So, anyway, so it is like emitting all these waves, right? And because it's moving away, the waves are just bigger. Okay, and meaning that the frequency is less, and that is why the frequency of the listener is less than the frequency of the ambulance itself, okay, of the siren. So here we have 550 hertz and the velocity is 25 meters per second. All right, yeah, I think we have everything we need here. So let's just go to 6.1.1. It says, states the Doppler effect in words, probably for 2 marks. Yes. Yeah, so basically, guys, the Doppler effect is the change in frequency of the sound that is detected by a listener, because the sound source and the listener have different velocities relative to the medium of sound propagation. Okay. If you can explain that in your own words, that would be great. If you can cram, that's also great. But that's the definition. Now 6.1.2, it says use the given information to calculate the speed of sound in air. All right, so what is the formula for Doppler effect? Okay, so we have here frequency of the listener is equal to the velocity in air plus minus the velocity of the listener And then in the denominator, plus minus the velocity of the source times the frequency of the source. All right, so now when we calculate this, you must ask yourself, where's the positive, where's the negative in the numerator and the denominator? But the frequency of the listener, let's just put in what we know. It's 512,64. And this velocity is what we're trying to find, the speed of sound in air. Now, because the listener is stationary, we're just going to put V on top. So leave it at that. And then in the denominator, we're going to use a plus or a minus. So remember, if the source is moving towards the listener, it is a negative. But if the source is moving away, then it is a positive. So the source is moving away, so we're going to use a positive. And then the speed of the source is 25 meters per second. And then the frequency of the source is 550. So here, let's do some mathematics, gymnastics, and see where that ends up. So we have 512,64 divided by 550 multiplied by the speed plus 25, and that's equal to the speed. So we have 512,64 divided by 550 times V plus 512,64 divided by 550 times 25 is equal to V. I'm going to put all the V's together. So V minus 512,64V over 550. So basically, I've taken this to the other side, but I prefer writing my unknowns on the left side of the equation. So please don't be startled by what I'm doing here. And then divided by 550 times 25. Okay, now we can start. Let me just remove this. We can then start calculating. So I have 1. I'm going to take this as 1V. Okay, 1 minus 512,64 divided by 550. And that's... Let me just write the fraction form. 467,6875 V is equal to, so I have 512,64 times 25 divided by 550. I'm also just going to use fractions, 6408 over 275. So now the velocity or the speed of sound in air, I'm just going to take this value over here and divide it by 467 over 6875. And what do we get there? 343,04. And normally they like giving us the speed of sound in air. So it's normally between 340 and 343. So I would be very confident if I got this answer when I calculated. Okay. Yeah. Now 6.1.3. So it says if the ambulance moves away from the stationary listener with a constant velocity which is greater than 25 meters per second. So now it's speeding off. How will each of the following change? Choose from increase, decrease, or remains the same. So if this ambulance decides to speed off, what will happen to the speed of sound in air? The speed of sound in air remains the same. Okay. Let me just write there. It'll basically remain the same. The speed of air is the speed of air. Speed of sound in air is the speed of sound in air regardless. So it remains the same. Now B, what will happen to the frequency of sound waves emitted by the siren? Okay, frequency of sound waves emitted by the siren. Sometimes if you're not certain, Just remind yourself, what is the formula for frequency? Okay, let's see. So you see that speed is frequency times wavelength. And now frequency would be equal to speed over wavelength. Okay, now let's get back to the question at hand. Okay, the frequency of sound waves emitted by the siren. So now we are speeding up, remember? If you're going to increase the speed, you're also going to increase the frequency. So therefore, the frequency, it will increase. Oh, my little friend who was supposed to be sleeping. And now the frequency of the sound waves detected by the listener, that one is obvious. It will definitely decrease. Okay, because this ambulance is moving away from the stationary listener, so it will decrease. Okay, we're almost there. Hang in there. The spectrum of a distant star when viewed from the Earth is red-shifted. Okay, remember, when it comes to red, we have a higher wavelength, therefore lower frequency. Just saying. Now 6.2.1, let me just remove this. So this is just 6.2. Okay, so 6.2.1 is the star moving away from or towards the Earth. So with the red shift, it is moving away because why? The wavelength is higher. 6.2.2. Use the Doppler effect to explain the answer to question 6.2.1. So basically, if you're moving away, the wavelength would have increased, right? The distance between the wavelength would have increased. And because we know that the wavelength is inversely proportional to the frequency, we know that the frequency is less in this case. Okay, so when we have redshift, lower frequency, higher wavelength, then the bigger the distance is. All right, so yeah, that's how I'd use Doppler effect to explain this answer, basically. And that is it for question 6. If you have any questions, any comments, better explanations, please comment down below. Question 7. All right, so it says 2-point charges A and B, each with a charge of positive 3 times 10 to the negative 9 coulomb, or you could say 3 nanocoulomb, are stationary on a horizontal surface. Point P is R meters from charge A and 2 R meters from charge B, as shown in the diagram below. So we can see that quite well. And you can go ahead and answer the question. So it says, describe an electric field. Now be very careful. They're not asking you to describe an electrical field at a point. It's just describing an electric field. So basically, an electric field, it is a region of space where an electric charge will experience an electrostatic force. Okay, so in summary, it's a region where an electric charge will experience an electrostatic force. And then 7.2, draw the resultant electric field pattern due to charges A and B. Okay, so both A and B are positive, and as such, they will repel one another. Okay, so if they repel one another, you're going to have, remember how we start electric field lines, they must first be perpendicular to the surface, and then you can go ahead and draw them out. Okay, and because they're positively charged, there will be, the direction is outward, okay, from inside outwards. Yeah, so basically that would be that. And because they are equal in magnitude, I would just give the same number of lines for each. Okay, but that's basically that for 3 marks. And then now they tell us that the magnitude of the net electric field at point P is 27 Newton per coulomb. Okay, so 7.3, calculate the value of R. Okay, So looking at our formula sheet, I mean, if you know these formulas off by heart, that is great. But if you don't, please check. Don't just assume that you know. Okay, so basically the net, that's K times Q over R squared. Let's just go back to the question 7. Okay, the net electric field. So they told us that is the net electric field is 27. But before we even go there, we first need to write down for A and as well as B. So basically, we have the electric field for A as well as B. Okay, sorry about that. And here I wrote A again. I just wanted to put B. So if I look at my lines that I drew, okay, you can see these ones are starting to go to the left and then push away, right? And these are going to the right and they push away. So in this case, my A will be positive if I'm taking right as positive, and B will be negative. Okay, just in case you're asking yourself why I start using positive and negative. So the K value will be 9 times 10 to the power 9. And for A, it is 3 times 10 to the negative 9. Okay, and that will just be R, okay, in relation to P, so it's just R squared. And then when it comes to B, we have a negative there, so 9 times 10 to the 9, again, times 3 times 10 to the power negative 9, right? And that will be divided by 2R squared. Remember to put that in brackets so that you don't just square the R, but the 2 as well needs to be squared. And the net electric field is 27 newtons per coulomb. All right, so now let us just see how we can simplify. So we have 27, 9 times 10 to the 9. Oh, here we go. So 9 times 10 to the 9 times 3 times 10 to the negative 9. That's just 18. Okay. I don't know why in my mind I expected, oh yeah, 3. I'm expecting 27. Yes, because the 10 to the 9 will cancel. Then you have 9 times 3, which is 27 over R squared. And then same thing again, minus 27 over 4 R squared. All right, so now I'm going to multiply throughout by 4R squared. Let's see what happens if I do that. Okay, so 4R squared, I will have 27 times 4R squared. Then I will have 4 times 27. Then I'll have minus 27. So now 27 times 4, that is 108 R squared. So I'll have 108 minus 27. So now R squared. So I have 108 minus 27, which is 81. And then we have 81 divided by 108. And I'm going to square both sides so that I can get what R is. And R has to be a positive value. I know when you square root, you're going to either have positive or negative, but this side we're just taking the positive answer. So now we have root 3 over 2. Okay, but let's just write it out in decimal form. So R is 0.87 meters. But wait, what were we looking for? Ah, yes, we want the value of R. You know when you calculate and you're wondering, what am I doing here? Yeah, so yes, R is 0.87 meters. Now 7.4. It says, calculate the magnitude of the net electrostatic force that an electron would experience if placed at point P, okay, what would it experience? The net electrostatic force. So there, looking at the formulas that we have two equations that have force in it when it comes to the section. So you either have the first one where force is equal to K, Q1, Q2 R squared, but I don't want to go with that one. I would rather go with this equation where we have F over Q, okay? And this Q over here, because we're now looking specifically at an electron that is placed near P, that will be the charge of an electron. And I hope you remember, but even if you forgot what the charge of an electron is, it's here in your formula sheet. The charge on an electron is negative 1,6 times 10 to the negative 19, but we're not going to put the negative portion on it. So just 1,6 times 10 to the power negative 19. And then we have the force over there. And we know that so let's just get back to the question. Question 7. We know that the electric field at point P is 27, okay, newtons per coulomb. So now our force is just simply going to be 27 times 1,6 times 10 to the power negative 19. And if we calculate that, so that's 27 multiplied by 1,6 times 10 to the power negative 19. And that gives us 432 times 10 to the negative 20. Okay, and that's force, so that is Newton. Okay, and that is it for question 7. Someone is busy dying here from milk. We are almost drawing near to the end. Question 8. The circuit diagram below shows a battery with an EMF of 12 volts and an internal resistance of 0.5 ohm connected to 3 resistors, a light bulb, a switch, an ammeter, and connecting wires. The ammeter and connecting wires have negligible resistance. Okay, so what do we know so far? The EMF is 12 volts. We have an internal resistor of 0.5 ohm. And yeah, okay. So now 8.1 says, state Ohm's law in words. Okay, so Ohm's law, basically the potential difference across a conductor is directly proportional to the current in the conductor at constant temperature. It's quite important for you to state that it's at constant temperature. Okay, so also to remember, potential difference is directly proportional to the current. But if you want to be more specific, you say potential difference across a conductor is directly proportional to the current in the conductor at constant temperature. All right, now before we get to 8.2, they tell us that switch S is initially closed. So 8.2.1, calculate the total external resistance in the circuit. Okay, so we see here we have this resistor that is in parallel. So R1 is parallel to R2. Okay, and then both of them are in series to RL. And ultimately, all of that is in parallel to R3. Okay, so I'm going to start with the parallel ones first. So we can see that we have 10 ohm and we have 10 ohm. If it's not so obvious to you that the resultant, if you were to now make it in series, if it's not obvious to you that this is actually 5 ohm, if this is 10 and that's 10, okay, then you can go calculate it. Please calculate everything so that you are sure. So let's do that. Let's just pretend we don't know. So 1 over the parallel resistance will be 1 over 10, which is 1 over R1 plus 1 over R2. All right, we have the same denominator. So that will just be the same denominator. We can add the numerators, which is 2. And then if you want the parallel resistance there, it'll just be 10 over 2, we just swap it around. Therefore, that parallel resistance is 5 ohm. Okay, now what are we left with? We have the 5 ohm resistor in series with the 10 ohm resistor, and all of that is parallel to the 15 ohm resistor. Okay, so then we're going to add the 5 and the 10, right? So we have our parallel over there plus the resistor L, which is now going to be 5 plus 10. So now that gives us 15 ohms. So now again we have 15 ohms. Okay, and we have another 15 ohms. It's just me simplifying the circuit. Okay. It's going to be something like this. And switch S there. Okay. So now we have 15 ohm, 15 ohm. Like you saw, the resultant resistance, which is now here. And we have our ammeter there and our battery. Oh my gosh. Yeah. So basically that would be 7.5 ohm. And where does that come from? Again, 1 over the parallel resistance will be 1 over 15 plus 1 over 15, which is basically saying 15 divided by 2. Okay, that's 2 over 15, 1 over parallel resistance. And now that parallel resistance is just 15 over 2 or 7.5. Okay, so basically that is the external resistance. So the total external resistance is equal to 7.5 ohm. All right, that was what? 3 marks? 5 marks. Yeah, Shem, we did work a bit there. Now we get to 8.2.2. So they say, calculate the reading on the ammeter. All right, so this is where now our EMF calculation comes in. Okay, you can go to the formula sheet. I just happen to remember it. So the current is basically the EMF divided by our external resistance plus the internal resistance. Okay, and that we did summarize it on top there, that the internal resistance is 0.5 and the EMF is 12. And we just calculated the external resistance. So we have 12 divided by 7.5 plus 0.5. Okay, which is just the same as 12 divided by 8. And what is 12 divided by 8? It's basically 1.5 amperes. Okay, so that is the reading on the ammeter. All right, and now 8.2.3. It says the power dissipated by resistor R3. Remember, resistor R3 is 15 ohm. Now with power, remember power is equal to V times I, but there are different variations to it depending on what you have. So we have the current, we have the resistance. So I would change V and put it in terms of I and R, and as a result, you get I squared times R. Okay, you can see that formula right over there. Okay, so now getting back to our question 8. What is the current that we calculated? Well, we calculated 1.5, and that will be squared. And what's the resistance there? R3, that's actually 15. So 1.5 squared times 15 gives us 33, yes, what did I say? Yeah, 1.5 squared times 15. Oh, wait. Ooh, please, before I make a mistake here, the current will divide. Okay, remember, ultimately we have, when we resolved this. So if it's one resistor, we're going to just put it like that, and that's 15 ohm, and then we have another 15 ohm, right? So if you have a current, remember this is the positive side, negative side, so the current moves like that. If the current reaches this point, it will have to divide, right? A portion of it goes there, and a portion of it, another portion of it goes there. Let me just use different colored pens. Okay, so this is our current. Once it reaches here, one portion goes there, the other portion goes there. And how this is divided will depend on the strength of the resistance. So because it's equal, your current as well, it comes in as 1,5 amperes, but as soon as it gets divided, it will actually divide by 2. So you're going to get 0,75 and then 0,75 amperes going through, and then it will meet up again, okay, over here, and becomes 1,5 amperes again. So with this power that we just calculated, actually this current here should be divided by 2, and it's divided by 2 because we can see it's a perfect 15 ohm and a 15 ohm. If it were different numbers, we'd calculate it differently. All right, so let's just say 1,5 divided by 2. And so let's go back and say this 1,5 actually divided by 2 should be squared. And then multiply that by 15. 8,44 watts, because this is power. Okay, something to always remember. I had forgotten there for a bit. So we're done with 8.2. Now we go to 8.3. Switch S is finally closed. No, switch S is now opened. If the resistance of the light bulb remains the same, how will the brightness of the light bulb be affected? Okay, so when it comes to brightness of light bulbs, so if we had these resistors connected in series, power would actually be directly proportional to the resistance. Okay, so if your external resistance increased, then the power would also increase, meaning the brightness would increase. Now, if they are in parallel, like we have here, power is actually directly proportional to the inverse of the resistance. So if ever your external resistance increases, then your power would decrease, therefore your brightness would decrease. So what do we have here? 8.3.1. The resistance of the light bulb remains constant. Okay, so remember when we resolved those resistor 1 and resistor 2, we then had 5 ohm, and then for the light bulb, we have our 10 ohm. Okay, and then now looking at our current. So our current comes guns blazing at 1.5 amperes. And then when it gets here, it wants to divide, right? But now switch S is open, meaning there won't be any current going through here. So, somewhat we're expecting the current here to increase. That's going through the 10 ohm as well as the 5 ohm resistance. So here, remember initially, our external resistance, we calculated it to be 7.5. Okay, total external resistance was 7.5 ohm. But now that the current is not passing through here anymore, now our external resistance would be 10 plus 5, which is 15 ohm. Okay, so in here, what are we saying? We're saying our external resistance, looking at this parallel connection, it has increased, therefore the power would have reduced and the brightness will reduce. So now 8.3.1, how will the brightness of the light bulb be affected? Well, basically, it will decrease. And 8.3.2, I think I started with that. It says explain your answer to question 8.3.1. This whole explanation actually accompanied by some bit of calculation. That is why I say that the brightness will reduce. It's because you have this resistor in parallel with that one. So your external resistance would have increased, and because they are connected in parallel, okay, like I said, this is for parallel connection, this is for series connection. Because we're focusing on the parallel connection, the power is inversely proportional to resistance, and power is like a measure of brightness. So the lower the power, the lower the brightness. Okay, and that's how it goes. And we are done with question 8. Second last question, question 9. All right, so we have a simplified diagram of a DC electric motor. Okay, so DC, direct current, electric motor. So it's a motor, left-hand rule applying. Okay, applicable here. So 9.1.1, it says write down the name of component A. We can see that that component is split, right? So it would be a split ring. Yeah, it's like a ring has been split. A split ring commutator. That is synonymous with the DC motor or generator. If it was AC, you would see a slip ring. Now it says state the energy conversion that takes place in a motor. If you forget, a motor turns, well, you require electricity in order for there to be motion. Okay, so basically we're going from electrical to mechanical energy. All right. And then 9.1.3. In which direction will the coil rotate? Choose from clockwise or anti-clockwise. Remember here we're using the left-hand rule. Now we are going from north to south. So your index finger is pointing to the left. Okay. And then we see that our current, this is positive, that's negative, so our current is going in this direction. The direction of the current is indicated by the middle finger. Okay, so if you have your index finger pointing to the left, north to south, and you have your current going inward, right, on the left side, your thumb is pointing upward, isn't it? So if it's pointing upward this side, it's pointing downwards on the other side. So in this case, it's going clockwise. Okay, so here, clockwise. Guys, if you decide to use the right hand, then this will be wrong. So be careful. When it comes to motors, we're dealing with the left-hand rule. When it comes to generators, we're dealing with the right-hand rule. Okay, so definitely going clockwise. And then 9.1.4. Okay, so it says state 2 changes that can be made to the motor for the coil to rotate faster. So if you want your coil to rotate faster, what you're going to do, you can increase the magnetic field strength. Okay, that's one of the ways you can do it. I think this I'll write down. So you can increase your magnetic strength, magnetic flux. Or what you can do is increase the number of turns, double it, triple it, whatever. But yeah, you can increase the number of turns. Okay, and the coil will rotate faster. Okay, you can also increase the strength of the current as well. All right, so yeah, increase the speed, whatever, but they wanted to, so that will do. So that is question 9.1. Okay, now we have 9.2. Okay. All right, so with 9.2, okay, let me just read what's happening there first. So the circuit diagram below shows an electric kettle and a toaster connected to an AC source with an RMS voltage of 220 volts. Okay, so that's something that you should please note, the RMS voltage. All right, and then the ammeter, connecting wires, and switches S and 1 have negligible resistance. All right, okay, so now the first question, which is asked, says define the term root mean square. So yeah, this definition, honestly, sometimes I kind of forget it or it's difficult to sort of like put it in words specifically, but basically the root mean square, it's to say, how can I put it? So you're representing the direct current that dissipates the same amount of power as the average power dissipated by the alternating current. Okay, so yeah, let me try to write this down. So basically, RMS, root mean square, in this case current, so the root mean square current of an alternating current. Well, yeah, so it's applicable to alternating current only, né? So the root mean squared current of an alternating current, it represents the direct current that dissipates the same amount of power as the average power dissipated by the alternating current. Okay, so the RMS current of an alternating current, it represents the direct current that dissipates the same amount of power as the average power dissipated by the alternating current. Okay, RMS values are used for voltage and current when dealing with alternating current. All right, so I hope that is a bit clear. And then 9.2.2, when switch S1 is closed, switch S1 is open. The maximum current through the circuit is 3.6. Okay, so now 9.2.2, calculate the root mean square current in the circuit. All right, we can go have a look at the formula sheet. Root mean squared current. Okay, there it is at the bottom. So we have the root mean squared current, which is equal to the maximum over root 2. Okay, so now let's go back up and get our maximum current, which they told us about. Okay, so it is 3.6. So we have 3.6 divided by root 2. And that would be it's 2.55 amperes. All right, and then 9.2.3. all right, so now it says when switch S1 is open, all right, and switch S2 is closed, the root mean squared current in the circuit is 2.62. So IRMS is now 2.62 amperes. Now calculate the energy consumed by the toaster in 2 minutes. So whenever we think about energy, I think about the power equation where power is work done per unit time, right? But since they're asking for energy, if power is work done per unit time, it means then the energy is basically equal to power times time. Okay, so now power, remember we have several equations for it. We have voltage times current. If you have resistance, then you can deal with that. But just a reminder, what they've given us over here is the voltage, which is 220. So I would go with the definition of voltage times current. All right, and the voltage that we have been given is 220. The current as well, they told us, is 2,62, and the time is 2 minutes, but we're going to use seconds, so 120 seconds. Okay, and so now when we calculate, we have 220 times 2,62 times 120, and then our energy is 69,168, and that would be in joules. And that concludes question 9 out of 14 marks. We are officially at the last question. So 10.1. Two small spheres A and B made of pure zinc are at rest 0,1 meters apart on a wooden table. Sphere A is negatively charged and is free to move on the table, while sphere B is uncharged and fixed to the table, as shown in the diagram below. Okay, this is giving question 7 vibes with electrostatics, but anyway. So now high intensity ultraviolet light of frequency 2,8 times 10 to the 16 hertz is now shone continuously onto sphere B. The work function of zinc is 6,63 times 10 to the negative 19 joules. Okay, so 10.1.1. First question asks, define the term work function of a metal. All right, so the work function is basically the minimum energy that an electron in the metal needs to be emitted from the metal surface. Okay, we normally indicate that with W subscript O or 0. Okay, so basically the minimum energy that an electron needs in order to be emitted from the metal surface. The electron in the metal, not from anywhere else. The electron has to be from the metal. Okay, so that's that. 10.1.2, it says explain using a suitable calculation why the ultraviolet light shone on sphere B will eject electrons from its surface. Okay, so what we have then, let's use the equation of the work function equal to Planck's constant times the threshold frequency. And basically, our work function, they told us that it's 6,63. Or before I even, let's just do that. 6,63 times 10 to the power negative 19. We have Planck's constant. Let me just check again. It's 6,63 times 10 to the negative 34. Okay, so we have it. Now back to the question. And let's calculate the threshold frequency. They already gave us the frequency of 2,8, right? In order for the electrons to be ejected, the frequency that we have has to be less. The threshold frequency has to be less than 2.8. If it's more than 2.8, then no electrons will be ejected. But anyway, let's just see. So threshold frequency is 6,63 times 10 to the negative 19 divided by 6,63 times 10 to the negative 34. I hope that you see that things are gonna work out, but let's just calculate. So 6,63 times 10 to the power negative 19 all over 6,63 times 10 to the power negative 34. We get 1 times 10 to the 15. Okay, so that is actually, you see now, the threshold frequency is actually less than the frequency of 2,8, because we have 1 times 10 to the 15, which is less than 2,8 times 10 to the power 16 hertz. Okay, so again, the question was saying, explain using a suitable calculation why the ultraviolet light shone on sphere B will eject. It will eject because the frequency is higher than the threshold frequency. You could have also calculated the energy, okay? And if the energy there was higher than the work function, then that would also work out. And now 10.1.3. So it says, sphere A carries a charge of negative 5.4 times 10 to the negative 6 coulomb, or negative 5.4 microcoulomb, and requires a minimum force of 0.027 Newton to move from rest. Calculate the minimum number of photons of ultraviolet light that must strike sphere B, which will cause sphere A to move from its rest position. Okay, so I'm already seeing forces here in my mind. Again, question 7 vibes, electrostatics. They also want to know the number of photons. Remember, photons are electrons that carry photoelectric, or that have, yeah, photoelectricness to it. So we're dealing with electrons over here. Okay, so let's look. Can we calculate the number of electrons? We should be able to. There should be a formula. It would be charge over the charge of an electron. There it is. So number of electrons, I'm going to put it like this. Okay, it's equal to the charge divided by the charge of an electron. Let me use small qe. And the charge of an electron, while we're at it, the charge of an electron, or on an electron, is 1,6 times 10 to the power negative 19. So now we need to get this charge. Let's go back to the question. So it says, calculate the number of photons of ultraviolet light that must strike sphere B. So we need to get the charge of sphere B. Okay, and they've given us a force. Okay, so let's just write there. We have a force of 0.027 Newton. And we have charge of sphere A, that is negative 5.4 times 10 to the negative 6 coulomb. All right, now let's go back to the formula sheet and see what formula can we use that has both, not here. Yes, it has force and it requires 2 charges. So yeah, that is the equation that I'm going to use. So the force is equal to K, charge of A, charge of B, and R squared. Okay, let's go back to our diagram so that we can see what the distance is, because I have forgotten. All right, so the force they said is 0.027. K is 9 times 10 to the power 10. Charge on A they gave us. We don't have to put in the negative sign. And then charge on B is what we're looking for. And the distance is 0.1. And all of that is squared. Okay, so our unknown is the charge on B. So what we're going to have is 0.027 times 0.1 squared. And then we're going to divide by 9 times 10 to the 9 times 5.4 times 10 to the negative 6. So let us see this neutral charge, or what this charge is. 0.027 times 0.1 squared divided by 9 times 10 to the 9 times 5.4 times 10 to the negative 6. Whew. Why is it giving me this answer like this? Okay, cool. So what am I getting? I'm just gonna say 5.56. So let me just count backwards. I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So times 10 to to the power negative 9. My word, this calculator is like, I don't know why it's not putting it in scientific notation. Jeez. Okay, now we go back and let's see. The charge, we have it as 5,56. Now I'm tempted to go take my Casio calculator and calculate here by hand because I'm not trusting if I actually did it correctly. I will just go. I'll probably pause after getting an answer and then just check again with my Casio calculator, and then we'll see. So the answer divided by 1,6 times 10 to the power negative 19. Why is it doing this to me? It used to give answers in scientific notation. Okay, so I'm going to say 3,47. And I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 3,47 times 10 to the power 10 electrons. Can someone confirm that? Okay, I'm just going to pause and go get my Casio calculator and just confirm. Okay, so I checked and I also changed this to scientific notation. So we were right, it's 5,56 times 10 to the negative 9. And if we take that answer, we divide it by 1,6 times 10 to the power negative 19. We get 3,47 times 10 to the power 10 electrons. Okay, they should be, that number, that exponent should be positive, right? Because electrons should be many. You shouldn't be getting any negative exponent. All right, so that's 10.1.3. We found the answer. It is 3,47 times 10 to the power 10 electrons. Now we can move on to 10.2. The last section, then we can call it a day. So it says a beam of white light is shone through a cold gas. The emerging light is dispersed and a line spectrum is observed on a screen. Okay, now it says 10.2.1. Name the type of line spectrum observed. Remember the type of spectrum you have? You have continuous spectrum. There's no line there. Then you have an emission spectrum. And you also have an absorption spectrum. So when it comes to white light that is shone through a cold gas, please, this one would be referring to the absorption spectrum. Okay, if you're not sure, you can just have a look at the video that I recorded in the playlist. It's part of the Doppler effect, but the application of it, which is the red and blue shift. Okay, so just have a look at it and I explain there nicely. So yes, we have the absorption spectrum. Then 10.2.2. Describe the spectrum referred to in question 10.2.1. Okay, so with the absorption spectrum, all right, like I said, or like they said in the introduction, you have a white light that passes through cold gas, and the energy of some frequencies of light is absorbed by the electron in the gas. Okay, so the electrons in the gas will absorb some of the energy, or rather the energy of some frequencies of light. Okay. Yeah, I'm thinking, should I write that down? So while you pass white light through the cold gas, the electrons in the gas, okay, the electrons in that gas, or we'll call it a cold gas, the electrons in the cold gas, what they do, they absorb the energy of some of the frequencies of the light. Okay, electrons in cold gas absorb the energy of some of the frequencies of that light. Yeah, the electrons in the cold gas absorb energy of some of the frequencies in that light. And another thing is the atoms then make transitions from lower energy levels to higher energy levels. Okay, so now the atoms there, they make transitions from, a lower energy level, I'm just going to say EL, lower energy level to a higher energy level. Okay, and that's that. Now 10.2.3 says, the diagrams below indicate some possible energy transitions made by atoms. Which one of the diagrams could result in the type of spectrum observed in question 10.2.1? So, like we said, the atoms make transitions from lower energy levels to higher energy levels. So therefore, diagram B would work better because we see we're going from lower energy to a higher energy. For diagram A, that would be emission spectrum, okay, because it goes from high energy to a lower energy. As it goes from high energy to lower energy, it emits, okay, it emits the energy. So that's why it's called the emission spectrum. Here, for you to go from a lower energy to a higher energy, you need to absorb the energy, okay, hence we talked about the absorption of energy there. So that is it for this physics paper. Okay, thank you for joining and tuning in. Don't forget to tell your friends about this channel, especially for those of you doing matric this year. We've done a whole lot of past papers, so you can use this YouTube channel as a way to revise. Please start now. You can see that we're posting these memos now in January as class has already begun. So whatever topic you're doing in class, look at the questions that are relevant. Use past papers to study, okay? Don't bother too much with textbook questions. Look at questions that were asked previously. All right, thank you.